Thanks so much for joining the Santa Fe Watershed Association as we explore the important relationships between soil and water within the context of the Santa Fe River watershed.
My name is Aaron Kaufman.
I'm Maury Hensley. Today, we are in the Upper Santa Fe Watershed with hydrologist Aaron Kaufman and fire ecologist Cody Stropke to learn a little bit about the history of this landscape and the linkages between soil health, municipal water security, fire management, and the 5 healthy soil principles. Whether your local soil lies within the boundaries of the Santa Fe River watershed or a different watershed, we hope that some of the concepts and histories we'll be discussing throughout the series will provide you with useful information and inspiration for your own explorations of soil and watershed stewardship.
The city of Santa Fe has 3 primary water sources. The main one is actually from the Rio Grande. It's water that's pumped uphill from the Buckman direct diversion, and it was kind of added as a water source about 15 years ago. The city also maintains a series of municipal wells when times are really dry. But one of the best water sources that we have is in the Upper Watershed, and it's with a couple of reservoirs. This is Nichols Reservoir behind me. McClure is up above us. But the benefit of these reservoirs is that we have a forested ecosystem with really good soils that essentially serve as a sponge. They help filter a lot of runoff, prevent a lot of sediment from making it down. So essentially what these soils are doing is they're providing a cheaper form of water for us to treat and provide for the community. The concern is that during a really good year, we might get 40 to 50% of our water from these reservoirs. But during dry years or in an event where we had a catastrophic wildfire, we could potentially compromise these water resources. And so that's one of the reasons we're doing what we can to manage forests in a way that protects these soils from erosion and potential sedimentation. Soil is composed of 4 primary ingredients. The first ingredient is the original kind of parent material, the original bedrock. It could be components of like old quartz, muscovite, things like that kind of decomposed into finer clays, but it is essentially the old lithic or bedrock material. The second primary ingredient is organic material, and that can include everything from the litter and duff layers. It's what we call it, basically the kind of the pine needles or old leaves that have fallen on the surface of the soil and are in the process of decomposing. It can also include some of the organic material in the actual soil further down, like fungal communities or mycorrhizal communities. You can see this kind of white material lower down in the soil profile. It can be old invertebrates, earthworms, things like that, as well as the decomposition of old animals that have passed away through this area. The final 2 ingredients are kind of what you would find in the pore space or the open areas in between the soil particles, and that would include either water or air. And so those are the 4 primary components: water, air, organic material, and the original parent material or bedrock. The 4 primary ingredients that we discussed are not kind of randomly distributed in a profile. Essentially what you have is that these ingredients that make up soils are kind of layered into what we call horizons. And so in an upper kind of watershed here in Santa Fe, in this forested area, you have your initial horizon, which is an O horizon. It refers to the organic material, and that's going to be kind of the undecomposed litter and duff layer, pine needles and leaf drop, old twigs, things like that. In a deciduous forest, it would be leaves and things like that. Then below that O layer, you start to get the formation of decomposition starting to happen, and that's called the A layer. You can see the finer material or structure being formed here through the decomposition process. Essentially the microbes that are in this upper soil layer over time are breaking down that organic material. Some of the things that they release, like sugars and other exudates, kind of sticky and tend to hold that soil together. This is really crucial for the purposes of storing water, which is important in this part of the watershed. Certainly retaining or slowing down water on these hill slopes, storing it in the soils for longer periods of time, allowing it to slowly release downstream is a benefit of kind of this part of the watershed. Below the A horizon, you have the formation of the B horizon. The B horizon is essentially a zone of illuviation, or basically the point at which a lot of minerals and salts and clays are accumulating. So essentially, oftentimes, because of that accumulation, you have a change in color. From the iron, you get kind of a red or rusty color. Up here in these forested soils, the B horizon is pretty deep, provides kind of a lot of decomposed material, but also essentially is providing kind of that sponge in the upper watershed where we can store a lot of water over time and have kind of a slower release down below. Sometimes right between the A and the B, you'll have something called the E horizon. It's called the zone of illuviation. Essentially what it is as water is moving through the soil surface, it's actually stripping some of the minerals and other materials out and leaving kind of a white layer. Not really seeing that around here as much. But essentially this would be your B horizon. This is kind of like more of the mineral material, a lot less of the organic material. That's why it's not nearly as dark in color. And then below that B horizon, you start to get into the kind of formation of the decomposition of the original bedrock. We call that the C horizon. That would be kind of what you'd notice is maybe sands and gravels, things like that. And then ultimately at the bottom you would have what's called a lithic structure, or the R horizon, and that is the original bedrock. The original components of bedrock up here are largely made up of schists and granite, and essentially through weathering processes they start to break down. So here you have the R horizon. This is the bedrock, or the original lithic structure. And with a little bit of weathering over time through freeze and thaw processes and the acidity from rain and snow, it starts to break that material down, and you end up with a C horizon on top of it. So this is kind of the broken down parent material. Over time, you're going to have the formation of the A's and the B's above it. Two of the healthy soil principles are to keep soil covered and to maintain a living root. The benefits of the upper watershed and some of the soils up here is that we have a good litter and duff layer, those needles that have kind of fallen out of the trees and accumulated on the ground. That basically provides some soil cover, and it reduces the impacts of raindrop impact and erosion that might occur during high intensity thunderstorms. The other benefit is as that material decomposes, it's starting to form the A layers underneath, which has really good soil structure due to that organic material. Provides a bit more of a sponge for holding and retaining water in the soil. And the nutrients from that decomposition process are beneficial because they help support that healthy root system of the various trees that you see here, as well as some of the willow and riparian vegetation you see behind me. Historically, in a ponderosa pine forest like this, you would have had fire moving through here every 5 to 15 years. There's been some changes in kind of like the late 1800s, essentially, through significant overgrazing. You would have lost the herbaceous understory, some of the grasses underneath these ponderosa pines, which would have carried surface fire across the landscape. And the other thing is you had kind of an increase in fuel loads, or basically trees, because of management policy which aimed to suppress or put fires out with consistency in kind of the late 1800s, early 1900s. What that's led to is an increase in the amount of fuels in terms of the overstory, and a decrease in the understory herbaceous layers from overgrazing. And so we still maintain some aspect of soil cover with the litter and duff layers here, which is beneficial in terms of reducing that raindrop impact, but we have less of the herbaceous layer, which would have provided much more continuous root structure to prevent soil erosion in this part of the watershed. There's been efforts in the last couple of decades in the upper watershed to remove some of that fuel through thinning processes of some of the trees that are too thick, and also kind of prescribed or controlled burns to kind of combust some of that fuel and remove it off of the soil surface, so that if we ever do have some sort of fire during conditions which would be lead to higher intensity or higher severity fires, it's a little easier to control or manage in order to protect our water resources.
The changes in the soils and the organic matter on the surface over the past 100 years have significant impacts on the downstream reservoirs when a fire were to occur. This is largely attributed to when you have a fire move through these areas, it burns really hot, results in the formation of a water repellent layer, which in turn increases the amount of erosion that takes sediment down to the streams, then it increases sedimentation into the reservoirs. When you have a fire that burns organic matter on the soil surface at a high temperature, you have a lot of the components in this organic matter gets broken down. At extreme heats, it gets volatilized, so this is actually turning into a gas. And what happens is you have these gases that are being released to the atmosphere, and they're also being distilled down into the soil profile. And what happens is you have these organic compounds that get into the soil profile where it's cooler than above, and these compounds coat the soil surface, which creates a hydrophobic layer. So essentially, it's almost like a tin roof. You have an impermeable layer down below the soil surface. So what happens when you get a precipitation event is you might get infiltration into the first few inches of a soil profile until it hits this water repellent layer, and then it, like I said, it's like a tin roof where you just get complete runoff, and it starts to create rill erosion, gully erosion, and a lot of issues. So the depth of the water repellent layer a lot of times is dependent on the surface temperature as well as the residence time of the fire. So the hotter the fire and the longer it burns in an area, the lower down the water repellent layer goes in the soil. And the water repellent layer is a big problem, as we mentioned earlier, because it doesn't allow the water to infiltrate down into that V horizon that would normally store the water. It actually runs off, and as it's running off, it's accumulating that top soil surface layer, that A horizon, and depositing it down into the channels and allowing that then to transfer down to the reservoirs as sediment, which will really result in a lack of functioning. You'll lose storage. It also will mess with water chemistry. When you burn the organic matter, you release a lot of chemicals and nutrients. A lot of nitrogen gets put into the system, which causes streams and reservoirs to become oxygen deprived. A lot of times you see a lot of fish kill and stuff like that after fire due to the large accumulations of sediment. It also, if you're using reservoirs for municipal water quality, it can affect taste of water. The sediment gets in the pipes and in the infrastructure and really causes a lot of problems. One way you can look at water repellency following a wildfire is you scrape all the ash away from the soil surface until you get to the bare mineral soil, and you take a drop of distilled water and you place it on the surface, and you count the amount of seconds that it takes for that water drop to infiltrate. When you have really strong water repellent soils, the water drop can stay on the soil surface for anywhere from minutes to days to weeks. Weak water repellent layers, usually the water drop will persist on the soil surface for 10 to 20 seconds, 30 seconds. So following a fire, you would have a continuous surface of water that would beat up. And this would persist until you got enough rains to start breaking down the water repellent layer. Over time, once you have moisture introduced into the system through the monsoon season and then through the freeze and thaw cycle in the winter, it helps to break down the water repellent layer so that it's not a continuous layer across the whole entire watershed.
To wrap up, here are some key takeaways from this video. While soil, water, and fire are intimately connected, as you can see, their relationship can be complicated. Ultimately, there is not necessarily one right way to manage a landscape, but rather a set of strategies that are optimized for many, sometimes contradictory, desired outcomes. In the case of the Upper Watershed, our primary goal is to protect the water security for the city of Santa Fe. Native groundwater and surface water from our local watershed is the cleanest, cheapest, and most precious water source. Soil water storage in the Upper Watershed, particularly in wetlands and forest soils, becomes even more critical as snowmelt occurs earlier in the year due to climate change. It's vital we ensure our community uses this water in a sustainable way, given climate projections. Protecting water storage capacity or sponginess in soils using our healthy soil principles will allow for a slower release of water downstream when it is needed, as opposed to rapidly running off the landscape in early spring prior to the growing season. We need to keep soil covered, but in the context of fire, it's important to think about how it is covered and with what. Frequent low-intensity fires can reduce soil cover in the short run, but minimize the risk of complete soil sterilization and hydrophobicity in the case of catastrophic fire. Similarly, in order to minimize disturbance in the long run, allowing low-intensity fire is important to avoid the extreme disturbance of catastrophic fire in the future. We need to maintain living roots, but in the case of tree density, less can sometimes be more. Plant assemblages are important to consider. Low-intensity prescribed burns can promote the germination of grasses and forbs, which are so important for maintaining soil health, but can get choked out by both too many trees and high-intensity fire. Maximizing biodiversity is always important, but in a municipal watershed, certain species provide more beneficial services than others. In the long run, semi-frequent low-intensity fire is an important part of this strategy. In this landscape, integrating animals has not been used in previous decades, but the legacy of mismanagement of domestic livestock is something that continues to shape the landscape. Improving habitat for ecosystem engineers such as beaver, however, can help promote more water storage and habitat for other species.
Thanks so much for watching. If you enjoyed this video, make sure to check out the rest of our series. See you around the watershed.